This lesson deals with supplemental problem 10.6. You can find this problem in the ECE202 ebook in the Chapter 10 Supplemental Problem starting at page 14. Given this integrator circuit, where I'm modeling the op-amp as a voltage-controlled voltage source with an open-loop gain of 100 million. I'm also giving the capacitor an initial condition of 0, although we're going to change the value of that shortly. You take this file and run it on PSpice and complete the following tasks. Could you plot the magnitude and angle of V out versus frequency? And then, using the techniques of Chapter 8 for phasor analysis, could you analyze this circuit and solve for the value of V out at 1 kHz? Do your results agree with part A1? Next, V out versus time and plot it. Then, using the Laplace transform techniques of Chapter 10, can you solve for V out at 1 kHz? Do your results agree with part B1? And lastly, change the initial condition in the PSpice file from 0 volts to 1 volt and repeat parts A and B. I ran the PSpice file and plotted the magnitude and the angle of node voltage 3, which was the output voltage. Now the file did analysis from 1 kHz to 10 kHz. I'm going to mark the values here at 1 kHz and we'll do the hand calculations using our phasor analysis techniques next. I found that the magnitude was 3.1831 volts and the angle was 0 degrees. Repeating this problem now with a phasor analysis, we need to transform from the time domain to the frequency domain. Our input was a sine wave with a magnitude of 2 volts. So I'll convert that to a cosine wave with the same magnitude but the angle of minus 90 degrees. Resistor is a resistor, but a capacitor has an impedance of minus j over omega c, where omega is 2 pi times 1 kilohertz, and our capacitor value is 0.1 microfarad. This turned out to be a minus j 1.5 K9 ohms. We have feedback around our op-amp, so if our op-amp's ideal, the current in here is 0 going in and coming out because the resistance is very high, and the voltage is driven to 0 because of the feedback. Let's analyze the problem. Apply a voltage, current's most likely going to flow, although it could be 0. I'll call that I1. Let's put it in this direction, although it's arbitrary, and we'll solve for it. With no voltage here, then all of V sub s is across Z1, and so the current would then be the voltage, which is 2 at angle minus 90, divided by the resistance of 1K. So 2 divided by 1,000 is 2 milli, and the angle is minus 90 degrees. Now that current flows up into this capacitor because there's no current here, and that creates a drop across the capacitor and go around the loop this way. So the rise in voltage would equal the drop of minus I1 times the impedance Z2 plus 0. And that's my value over here. So minus I1, and then the impedance is minus j 1.59K. I know the value of I1. I'm just going to plug that in over here. So that's 2 milli at angle minus 90. Multiply the magnitudes. Milli and the K cancel. So 2 times 1.59 is 3.1831. And the angle is going to be minus 90 plus 90 or 0. And that agrees with part A1. And then lastly, V out is also equal to minus Z2 divided by Z1 times V sub s. The PSpice file also had a transient analysis in it from 0 seconds to 2.5 milliseconds. And I plotted the output voltage, which is node voltage 3. And you can see that I've got a cosine wave that's offset with its highest value being 0 volts and its minimum minus 6.3622. Now let's analyze the circuit, see if we get the same results. Well, we've actually done this before in ECE201 in supplemental problem 6.1. So let me go grab the formula from that supplemental problem, which is equal to minus 1 over R1C2 integral from t0 to t V sub s of x dx minus the initial condition across the capacitor. Resistor was 1K, the capacitor was 0.1 microfarad. Started out at time t equals 0 to t. We had a 2 volt amplitude and had a sine of 1 kilohertz, and replaced t by x, and we had a 0 initial condition. Now the reciprocal of this turns out to be 10K, so I've got a minus 10K. Bring the scalar out in front too here, and the integral of sine is minus cosine, and so I get a minus sign from that, the cosine of the same argument, and then we've got to divide it by the derivative of this with respect to x, which is 2 pi times 1K. Then we're going to evaluate that from our upper limit to our lower limit. All of this multiplied out is 3.183 times the cosine evaluated at the upper limit, and then minus the value at the lower limit, but the cosine of 0 is equal to 1. I've got this term times 3.183, and I've got this times a minus 1. So my value is minus 3.183 plus 3.183 cosine of 2 pi 1kt. Now what's the largest negative value this is going to have? Well, it's minus 1. So if we take this and multiply it by minus 1 and add it to this, we get the result we have up here. We're pretty close to it. Next, let's do the analysis using the Laplace transform. Let's get our 5-step process. The first step is to find the initial conditions, which we already were given as 0. Second is to transform the circuit into the S domain. So our resistor is still a resistor, our op-amp is still an op-amp, but our capacitor is 1 over SC. And C was 0.1 microfarad, so the reciprocal of that is 10 to the 7th. Our input was a sine wave with an amplitude of 2. And so looking up in our table in chapter 9, that would be, for the sine wave, would be beta over s squared plus beta squared. Now beta was equal to 6.283k, in other words 2 pi times f, and then we have s squared, and then we have the same value here squared. Step 3 is to perform an S-domain analysis, and we showed in part A that the output was equal to minus z2 over z1 times v of s. Then our z2 was 1 over sc, which is going to be 10 to the 7th over s, as we calculated on the last page, divided by 1k, also have a minus sign. And then we have our 2 volt sine wave at 1 kilohertz, 6.283k divided by s squared plus that same quantity squared. Now all these constants turn out to be equal to 125.66 times 10 to the 6th, and if we square this, we get 39.48 times 10 to the 6th. Now since I have no s to the 1 term, this is just simply a pair of complex conjugate roots. So we take the square root of this, plus or minus j. Those will be our 2 roots. Let's just try it. So we take the square root of this, I'll get back 6.283k again, and then plus and minus j. So when you multiply this out, I'm going to get s squared, and I'll have this times s, and then I'll have the same thing times s, but with the opposite sign, so they'll cancel. And when you multiply this times this, we get that quantity squared, j squared, and a minus 1. So that turns out to be a plus 3.948 times 10 to the 6th. Now since the highest power in the numerator is s to the 0, and the denominator is s to the 3, we have a proper rational function, and we can do our partial fraction expansion. So then this can be written as some k1 over s plus some k2 over s minus j 6.283k, and then plus the conjugate of k2 divided by s plus j 6.283k. We'll take this expression and multiply it by s, and then let s equal 0. Term cancellation, so I get a minus 125.66 times 10 to the 6 divided by 39.48 times 10 to the 6, and that turns out to be a minus 3.183. Take the same quantity again and multiply it by s minus j 6.283k, and let s equal the positive value of that. We got the following. So we'll have this term canceling with this one. So minus 1.2566 times 10 to the 6 divided by s, which is going to be a plus j 6.283k. And then I've got j 6.283k here, so I've got that twice. And then I can multiply the j's together, get a minus sign. That's going to cancel this one. And all of those constants turn out to be 1.5915. You can also write that as having the magnitude of 1.5915 at an angle of 0. And so k2 conjugate is just going to have the opposite sign for theta. Now we can add our k1 over s, k2 over s minus j 6.283k, plus k2 conjugate over s plus j 6.283k. Our next step is to find the inverse Laplace transform. As we've shown previously, this is a step function whose strength is minus 3.813, and then this term together is a cosine of the frequency 2 pi times 1k, which is the 6.283k. The value we have out here in front is twice the magnitude of k, so that's 3.183, and then all of this is multiplied by u of t. This is the same equation we had in part B1. One last thing to note here, the phasor response doesn't predict the DC level in V out, even with 0 initial conditions. It's just taking a look at the AC part of the response. Our next task in part C was to change the initial condition from 0 volts to 1 volt. So run the simulation again. When you do the AC analysis, nothing changes because the phasor analysis doesn't predict DC levels. But for part B, we do get a little different result. This is the transient analysis. So we get the same AC part again, but we're offset by minus 1 volt. Let's figure out why that's happening. Our Laplace analysis technique will predict a complete response, so we can use this technique to explain what's happened in the last step of our simulation. So what we have to do is modify our S-domain circuit. We're adding it as an initial condition that's not 0. So we're going to replace our capacitor by a capacitor in series with a voltage source, whose value is a step of the initial condition, which would be 1 divided by S. Let's analyze the circuit. Now setting this source equal to 0, we're back to our previous circuit where we found the results in B2, and we'll have the same results, and that will be our output due to the first source. Now set this equal to 0, put a short circuit here, and let's analyze the second source. Setting this equal to 0 is a short. Getting a feedback around the op amp, so we drive the voltage to 0. And that means that the voltage across here is 0, so the current's equal to 0. So if we go around this loop, the rise in voltage would equal the drop, so it'd be minus 1 over S, and then minus the drop across here, which is going to be 0 times the impedance of the capacitor plus 0, and that's what I've written down over here. Now we can add the two results together. So our first result was this term over here. This is our 0 state response. And then we just found that we're going to add to that a minus 1 over S. Our inverse Laplace transform for this part would still be the same. But now for this part, I've got these two terms added together, really both subtracted. So I've got a minus 4.183 divided by s, and of course that in the time domain is a step whose amplitude is minus 4.183. Now when t is equal to 0, this is equal to 3.183, and added to this would give us a value of minus 1, and that was the value we had seen at t equals 0, and then when this becomes a minus 1, we get the negative value that's the sum of these two, which would be a minus 4.183 and then a minus 3.183. And this is supplemental problem 10.6.